And those core limestone blocks were already eroded when the granite blocks were put there. Why? Because the granite blocks have actually been purposefully and deliberately cut to fit into the erosion marks on the, we believe, much older megalithic blocks there. Physically speaking, copper and sand should never be able to slice through granite at the speed achieved by modern machinery. Yet an ancient drill core discovered in Egypt preserves compelling evidence that this seemingly impossible feat actually took place. The continuous spiral grooves etched into this artifact display a level of mechanical precision far beyond anything a hand-powered tool from antiquity could reasonably produce. Graham Hancock describes this piece as the final key needed to unlock the enduring mystery of how the Great Pyramids were constructed. He stands prepared to present the proof that could rewrite our understanding of the ancient world. The illusion of a Brazian standing before the massive granite blocks weighing tens of tons at the Giza Plateau or in the Valley Temple. The first question that springs to mind for anyone is always the same. How did they cut these? The official answer, taught in universities and printed in archaeology textbooks for more than a century, remains simple and consistent. Egyptologists assert that the pyramid builders possessed only the most primitive tools of the Bronze Age. They used copper chisels, copper saws, and most crucially, sand. This theory rests on the Mohs hardness scale, a standard measure in geology. Copper ranks as a soft metal. Around 3 on the Mohs scale, granite, the primary material of the King's Chamber in the Great Pyramid, is far harder, ranking 6 or 7. Physically, copper cannot cut granite. Attempt to slice granite with a copper blade, and the blade will wear down and deform long before leaving any mark on the stone. That is why quartz sand takes center stage in this explanation. Desert sand contains quartz with a hardness of 7 equal to or slightly exceeding that of granite. The mainstream explanation holds that the ancient Egyptians employed copper tubes or copper saw blades merely as carriers. They sprinkled sand into the cut and applied human power to rub back and forth continuously. The sharp-edged sand grains, trapped between the copper and the stone, acted as tiny blades, gradually grinding away the granite over thousands of hours of manual labor. It sounds plausible. In theory, with sufficient time and manpower, anything can be worn down. Yet, when we apply principles of modern mechanical engineering to analyze this process, a serious flaw emerges. The flaw lies in the very nature of abrasion. Abrasion with loose abrasive is an inherently chaotic process. Picture it at the microscopic level. The sand grains remain unbound. As the copper blade moves back and forth, the grains roll, slide, collide randomly, and spin freely. They strike the stone surface from unpredictable directions. This physical behavior is known as random impact. The inevitable outcome of such random impacts is a correspondingly random surface. When you sand wood with sandpaper or scour stone with sand, the result is a rough, matte finish covered in billions of overlapping scratches running in every direction. You cannot produce an optically flat surface or a razor-sharp cut simply by allowing sand grains to tumble freely. The chaos of the tool imprints itself on the final product. But here is where the physical evidence from Egyptian sites challenges this theory. When we examine granite artifacts closely at the Serapeum in Saqqara or the statues in the Luxor Temple, we find no trace of chaotic abrasion. The surfaces show no roughness or dullness. Instead, they are mirror smooth, reflecting light like glass. And most strikingly, their flatness reaches a level of precision imperceptible to the naked eye. The interior right angles inside the 100-ton granite boxes at the Serapeum appear so sharp that they seem assembled from glass panels rather than hollowed from solid stone. A loose sand abrasion process, reliant on human-powered back-and-forth motion, cannot maintain the geometric stability needed to create such crisp edges. Sand always tends to round corners due to uneven force distribution. To achieve razor-sharp right angles in hard stone, a tool with a fixed directional cut is required, not a loose mass of grinding powder in free motion. This contradiction presents a physical paradox right at the site. The copper and sand explanation describes a chaotic process. Yet the physical evidence reveals an outcome of remarkable order and high precision. If sand and copper produce rough surfaces, what technology created the glassy, flat surfaces we observe today? Materials science tells us that the character of a cut directly reflects the character of the tool. A ragged cut comes from a dull or loose blade. A smooth, precise cut comes from a sharp, stable edge. When we look at Egypt's granite blocks, we see no signs of random friction. We see evidence of deliberate, controlled cutting. To find the most compelling proof of this cutting, we cannot rely solely on polished exterior surfaces. We must look inside, at the removed stone portions that ancient craftsmen assumed no one would ever examine. That brings us to core drill number 7, the spiral path. In the late 19th century, Sir William Flinders Petrie, hailed as the father of modern archaeology, conducted a comprehensive survey at Giza. Unlike contemporary explorers obsessed with treasure or mummies, Petrie was fixated on measurements and engineering precision. He brought the most accurate surveying instruments of his era to measure the pyramids, and he became the first to collect discarded technical samples from the site. Stone drill cores. In 2, drilling a hollow hole. A tubular drill bit cuts into the stone and leaves a central stone cylinder behind. Once the work finishes, this core is snapped off and discarded. To most people, it was trash. To Petrie, it was data. He brought a collection of these cores back to England, and among them, the most famous is core drill number 7, a piece of red granite from Giza. When Petrie examined core drill number 7 under magnification, he discovered a physical feature that shook his assumptions about ancient technology. Running along the body of this cylindrical core were not random longitudinal or transverse scratches, as the sand and copper theory predicted. Instead, he found a continuous spiral groove. This groove runs steadily from top to bottom. Exactly like the thread on a modern screw, it spirals around the core, completing full 360-degree turns and continuing downward without interruption. In the language of mechanical engineering and machining, the difference between random scratches and a continuous spiral groove separates entirely different technological worlds. If sand abrasion were used, the grains would constantly shift position, even with steady rotation of the copper tube. The chaotic movement of thousands of sand particles would erase any trace of previous rotations. The result would be faint concentric circles or vertical scratches from raising and lowering the drill, but never a seamless, sharp, deep spiral groove. Like this, the presence of this spiral proves an entirely different physical mechanism, turning or controlled cutting. To produce a spiral groove in hard material, the cutting tool must satisfy 2 essential conditions. First, it requires a fixed cutting point. The tooth or edge penetrating the stone must remain stationary relative to the drill bit, not tumble freely like sand grains. Second, and more critically, this tool must be hard enough and backed by sufficient force to maintain its path while being driven deep into granite. Imagine a plow blade slicing through soil. The plow digs a deep furrow because it is harder than the earth and propelled by powerful force. The groove on core drill number 7 is the trace of just such a plow cutting through granite. The tool did not gently rub the surface. It plowed aggressively and decisively through the tough quartz crystal lattice of the granite. This is the fingerprint of positive displacement cutting force. It shows the drill advanced along a path under absolute geometric control, much like a diamond-tipped CNC drill today. Rather than the slow, tentative probing of manual methods, Petrie's discovery completely eliminates loose sand from the creation of this hole. Sand cannot produce screw-like threads. Only a rigid cutting edge, firmly attached to the drill bit, can achieve that. And this leads to an even more perplexing physical question. If not sand, what material from that era was hard enough to serve as the plow through granite? Copper certainly could not. Copper would deform instantly upon contacting granite under such pressure. But the issue extends beyond the tool's material. When modern engineers measured the spacing between the spiral grooves on core drill number 7, they uncovered a figure that would make any machining expert shudder. That figure reveals a truth about the applied force that mere human power could never generate. And with that, the story shifts from hard to believe to physically impossible. The paradox of pressure. Once we establish that the groove on core drill number 7 represents a continuous spiral cut, the unmistakable signature of a fixed cutting edge rather than loose tumbling sand, we must confront the quantitative data it carries. In mechanical engineering, the shape of a cut reveals the method. Yet the depth of that cut exposes the force behind it. And it is here that the numbers turn truly alarming. Sir William Flinders Petrie, along with later mechanical engineers such as Christopher Dunn, carefully measured the spacing between the spiral grooves on this granite core. In modern machining terminology, this spacing is known as the feed rate. It indicates precisely how far the drill advanced downward with each full 360-degree revolution. The measurements on core drill number 7 reveal a feed rate of 0, 1 inch, roughly 54 millimeters per revolution. To grasp just how extraordinary this figure is, consider a direct comparison with contemporary stone drilling technology. Industrial diamond drill bits today rotate at extremely high speeds, often thousands of revolutions per minute. Yet they penetrate granite only by tiny fractions of an inch per revolution. Modern strategy relies on high speed combined with low pressure to gradually wear away material without snapping the bit. The creators of core drill number 7, whether ancient Egyptians or some other hand, employed the exact opposite approach. Rotation speed may have been slower, but the cutting force was colossal. To drive a tubular drill bit tube, 5 millimeters deep into hard granite in a single revolution demands far more than the tool's own weight or the downward push of a single workman. The physics of granite dictate enormous resistance. To overcome that resistance and plow tube, 5 millimeters deep in an instant, the drill required an axial load equivalent to roughly 2 tons of downward pressure. Picture placing a full-size pickup truck atop a hollow copper tube and attempting to rotate it. What would happen? According to the principles of material strength, copper is soft and ductile under 2 tons of force. Even a thick-walled copper tube would undergo immediate plastic deformation. It would bulge, crumple, or twist like an empty soda can long before it could begin to scratch the granite surface. Structural failure of the tool itself would occur well before any meaningful cutting could take place. If we return to the sand hypothesis, the problem grows even more severe. Under 2 tons of concentrated pressure across the small contact area of the cutting edge, the quartz grains in the sand would no longer function as abrasives. They would be crushed into fine powder on contact. Sand only works as an abrasive when the grains remain intact and free to roll. Compressed under such tonnage, sand becomes a useless cushion that actually prevents direct contact between any cutting edge and the stone. Thus, the 1 inch figure stands as a silent confession from the material itself. It utterly eliminates the possibility of manual human power combined with copper tools. Human muscle cannot generate and sustain 2 tons of steady, uniform pressure while rotating a drill bit, and copper cannot withstand that pressure without catastrophic destruction. We are witnessing the traces of heavy-duty industrial machining. The cutting forces applied to this stone match those produced by powerful machinery, not biological muscle. Yet, if this immense pressure alone does not shatter conventional historical assumptions, the material state at the point of cutting delivers the final, decisive blow. The impossible material state. When we place core drill number 7 under an electron microscope to examine the microscopic structure of the cut groove, we enter territory where traditional hypotheses collapse entirely. This is the pivot point of the entire investigation, the moment when clinging to images of diligent stone-chiseling craftsmen becomes impossible. Granite is far from uniform. It forms as crystallized magma, a mixture of distinct minerals, primarily feldspar, mica, and quartz. Each mineral possesses a different hardness. Feldspar and mica are relatively softer, while quartz ranks extremely hard at 7 on the Mohs scale in any ordinary physical abrasion process, such as sand and copper. This hardness variation leaves unmistakable traces. Softer feldspar erodes faster, creating recessed areas. Harder quartz resists longer, protruding or, in many cases, getting plucked entirely from the matrix by frictional forces, leaving jagged pits. The resulting surface appears rough and uneven at the microscopic level. Yet, on the spiral groove of core drill number 7, this natural rule is violated. The groove slices through these differing mineral components with eerie smoothness and uniformity, showing no regard for hardness differences. It cuts feldspar and quartz to exactly the same depth with the same clean precision. No protrusions, no recesses, no plucked crystals appear. Even more startling, close examination of quartz crystals lying directly along the cut path reveals they have not fractured along their natural cleavage planes. Instead, they appear sliced or plastically deformed. In solid-state physics, quartz behaves as a brittle material. It typically shatters under impact. For quartz to be cleanly sliced or deformed without shattering, it requires an extraordinary combination of extreme heat and extreme pressure at the contact point. These conditions force granite into localized plastic deformation. In simpler terms, at the instant the drill passed through, the granite did not behave like hard stone. It responded like soft wax or pliable plastic. This phenomenon occurs in modern machining only when ultra-high-speed drills or intensely focused heat sources generate enough frictional energy to cause instantaneous localized melting at the cutting zone. The material softens just long enough for the tool to pass before cooling and rehardening. The conclusion becomes inescapable. The tool responsible for core drill number 7 was not merely harder than granite. It was a high-energy tool. It did not chip or grind. It penetrated matter itself. The copper chisel and wet sand hypothesis cannot account for the plastic deformation of quartz. Sand and water act as coolants, preventing temperature rise. Manual processes remain cold processes, yet the microscopic evidence points unmistakably to a high heat pressure process. At this juncture, we must acknowledge that the familiar portrait of slaves hauling stones falls short. Something far more advanced lies hidden here. A technology capable of manipulating the physical state of hard stone in ways humanity has only recently begun to achieve, and if the tool reached such sophistication, what force guided it? The missing skeleton. Even the sharpest laser scalpel in the world becomes useless in trembling hands. The precision of a cut depends not only on the sharpness of the blade, but absolutely on the stability of the hand that holds it. Physics teaches us a fundamental principle of precision machining. No product can be more accurate than the tool that creates it. To produce a perfectly regular spiral groove with an error smaller than 0.001 inch across granite, the cutting tool itself must be held stable at an equivalent or greater level of precision. The human body is a biological system riddled with chaotic vibrations. Our heartbeat creates tiny tremors. Fatigued muscles introduce shake. Breathing shifts posture. No craftsman, no matter how skilled, can hold a drill bit perfectly stable along its axis while applying 2 tons of compressive force and rotating it steadily. If a human hand directly controlled the tool, the drill would wobble. The resulting hole would never be perfectly round, and the spiral groove would become interrupted, offset, or vanish entirely due to random changes in angle. Yet core drill number 7, along with thousands of other drill holes found at sites such as Abuser, remains perfectly round and straight. The spiral groove runs unbroken. This geometric perfection demands the complete removal of human variability from the tool guidance process. Logic forces an unavoidable conclusion. A guidance mechanism must have existed. A frame, a machine. We are speaking here of the concept known as mechanical fixturing. To drive a drill bit deep into stone at a precise 90-degree angle while maintaining 2 tons of pressure, the bit had to be mounted in a rigid frame equipped with a fixed rotation axis and a drive system capable of converting energy into smooth, consistent rotary motion. The absence of these machines from the archaeological record, perhaps because they were made of perishable wood that decayed, or because they were dismantled and recycled, does not prove they never existed. The products they created, the drill cores, lie plainly before us. In forensic science, if you find a bullet embedded in a wall bearing distinctive rifling marks, you know with certainty that it was fired from a rifled barrel, even if the gun itself is never recovered. Core drill number 7 serves as exactly that bullet. It carries the characteristic signature of the rifled barrel, the machine that produced it. The existence of the bullet proves the existence of the gun. We confront the ghost of a vanished mechanical engineering tradition. The ancient Egyptians were not merely great architects, they were machinists. And if any doubt lingers about their mechanical sophistication, if you suspect the drill holes resulted from some fortunate accident, the next piece of evidence will dispel every remaining reservation. The aerodynamics of stone. Our investigation into ancient Egyptian stone machining capabilities now moves from microscopic cuts to a macroscopic object, an artifact that defies every assumption about hand carving, the schist disc of Sabu. Discovered in 1936 at Saqqara and dated to approximately 3000 BCE, even predating the Pyramid era, this object is crafted from metasilt stone or schist, a layered metamorphic stone that is extremely brittle and prone to shattering. Strike schist with a hammer and it does not chip away in controlled fragments. It fractures explosively or delaminates instantly. Yet the object before us is a perfectly round disc, roughly 61 centimeters in diameter, featuring a hollow central hub and 3 gracefully curved inward lobes that flow like silk. Its rims taper to edges so thin they defy belief. Imagine attempting to sculpt this shape from brittle schist using only a copper chisel and a stone hammer. Each hammer blow sends shock waves rippling through the material with such thin and intricate features. Those vibrations would shatter the delicate lobes long before the piece could be finished. The complex geometry stands as the mortal enemy of percussion carving. From a manufacturing perspective, this form can only be achieved through progressive abrasive machining or lathe turning, methods that remove material gently without sudden impacts and allow the tool to move at sufficient speed to slice cleanly through fragile layers. Even more astonishing than the material is the shape itself. Archaeologists label it a bowl or lamp, physically. However, it makes a terrible bowl. As liquid would spill through the wide openings between the lobes, it makes an equally poor lamp since the design obstructs light. To a modern engineer, the Sabu disc resembles nothing so much as a mechanical component, a flywheel, or a centrifugal impeller used in pumps. Its three curved lobes display clear aerodynamic properties, evidently designed to interact with fluids or gases during high-speed rotation. It speaks of motion, centrifugal force, mechanical function. The Sabu disc stands as the second piece of physical evidence, perfectly complementing core drill number 7. If the core proves the ability to cut hard materials with immense force, the disc proves the ability to shape brittle materials with exquisite complexity. Both demand control over matter far beyond unaided human hands and eyes. They are products of engineering thought, not mere decorative art. The verdict of physics, when we step back and survey the full picture from the microscopic spiral, grooves on core drill number 7 to the aerodynamic form of the Sabu disc. A stark truth emerges. These artifacts are no longer inert museum curiosities behind glass. They are surviving data recorders, black boxes left from a historical crash. The data they preserve, encoded in the language of friction, pressure, and crystal structure, tells a story radically different from the one we were taught. The laws of physics serve as impartial, incorruptible witnesses. They declare that creating these cuts required a technology capable of generating tons of pressure, delivering absolute directional control, and achieving cutting speeds fast enough to transform hard stone into something momentarily soft as wax. We need not invoke extraterrestrials or magic to explain this. Such explanations offer lazy escapes. The reality may prove far more astonishing. Our ancestors, flesh and blood, human beings, once attained peaks in materials, science, and mechanical engineering that we have since forgotten. They possessed a body of knowledge that allowed them to master the physical world in ways we have only rediscovered in recent centuries. The greatest question is no longer how they did it. Physics has already shown us what happened. A high-energy machining process. The haunting question now is why it vanished. Why would a civilization capable of turning granite like wood revert to crude stone-pounding tools in later centuries? Why did those great machines disappear without trace, leaving humanity adrift among colossal stones they could no longer shape? Core drill number 7 rests quietly in the Petrie Museum, a silent reminder of the fragility of knowledge. It proves that progress is not an unbroken upward line. We once reached extraordinary heights and we fell painfully far. So far that we forgot what we once knew. In the silence of the stone, we hear the echo of a lost legacy waiting once more to be understood.